At approximately 5:12 in the morning on April 18th, 1906, a sequence of motions began beneath Northern California that would redefine the understanding of earthquakes for generations. A smaller precursor shock rippled through the region, strong enough to wake residents across the San Francisco Bay Area. Then, within roughly 20 to 25 seconds, the main rupture broke free. What followed was not a single jolt, but a sustained period of violent ground motion lasting between 45 and 60 seconds. How could a fracture deep within the Earth propagate across nearly 300 miles in less than a minute? What mechanisms allowed sections of land to shift by tens of feet in seconds? And more than a century later, how much of that strain has quietly rebuilt beneath the same landscape? The event is now commonly described as a magnitude 7.7 to 7.9 earthquake, though earlier interpretations placed it at 8.3 on the Richter scale. The distinction reflects evolving measurement systems rather than any uncertainty about its scale. The rupture extended approximately 296 miles, or 477 kilometers, along the San Andreas Fault, from the vicinity of San Juan Bautista in the south to Cape Mendocino in the north. This length alone distinguishes the event from more recent earthquakes in California. The 1989 Loma Prieta earthquake, for example, involved a rupture of roughly 25 miles, or 40 kilometers, a fraction of the 1906 break. The speed of movement along the fault presents a striking contrast between human perception and geological processes. In areas where surface displacement approached 20 feet, or about 6 meters, the shift likely occurred over 4 to 5 seconds. That translates to a movement rate of roughly 4 to 5 feet per second, or about 1 to 1.5 meters per second, equivalent to approximately 3 miles per hour or 5 kilometers per hour. Yet the rupture itself, the propagating fracture tearing through the crust, travelled vastly faster at an estimated 2.7 kilometers per second, or about 5,800 miles per hour. This difference between slip velocity and rupture velocity is central to understanding how energy is transmitted during major earthquakes. Damage was not confined to a single urban centre. While San Francisco experienced extensive destruction, the effects were documented along the entire rupture zone. Coastal communities near Mendocino reported widespread failure of brick structures and chimney collapses, consistent with the vulnerability of unreinforced masonry to lateral shaking. Inland, the earthquake was felt as far north as southern Oregon, as far south as regions beyond Los Angeles, and eastward into central Nevada. The geographic reach underscores the scale of seismic waves generated by such a long rupture. Surface displacement measurements taken after the event revealed offsets of up to 20 feet near Point Reyes. Subsequent reanalysis of geodetic data suggests that deeper sections of the fault experienced even greater slip, with estimates of roughly 24 feet near Point Reyes and as much as 28 feet near Shelter Cove. In contrast, the southern 100 miles, or 160 kilometers, of the rupture showed smaller displacements averaging between 8 and 12 feet, or about 2.5 to 4 meters. This uneven distribution of slip illustrates how stress is not released uniformly along a fault, leaving some segments more strained than others even after a major event. Long before 1906, the fault system had already demonstrated its capacity for large earthquakes. Geological trenching studies have provided some of the clearest evidence. By excavating across the fault trace, researchers identified layers of soil disrupted by earlier ruptures. Within these layers, fragments of charcoal were discovered and dated to roughly 400 years before the 1906 event. This method, combined with similar studies across California and long historical records from regions such as China and Japan, reveals a broader pattern. Large earthquakes on major strike slip faults tend to recur over intervals measured in centuries rather than decades. Patterns observed before 1906 provide a useful comparison. In the 70 years leading up to that event, the region experienced frequent moderate earthquakes, with magnitudes between 6 and 7 occurring roughly every 10 to 15 years. The re-emergence of similar activity in the late 20th century suggests that the region may have entered another phase of heightened seismicity. This does not imply an imminent repeat of the 1906 rupture, but rather indicates a cycle in which stress is released through a series of smaller yet still damaging earthquakes. Attention has increasingly shifted toward other segments of the fault system that traverse densely populated areas. The Hayward Fault, running along the eastern side of San Francisco Bay, is often identified as one of the most concerning. A magnitude 7 earthquake on this fault today could result in hundreds of fatalities and economic losses approaching $100 billion. The Rogers Creek Fault, connected to the Hayward system, presents a similar risk profile, particularly because of its proximity to urban development. Urban growth since the early 20th century has dramatically altered the potential impact of earthquakes. In 1906, many areas along the fault were sparsely populated compared to today. Over the following decades, Northern California experienced extensive expansion, with infrastructure networks, residential zones, and commercial centers spreading across regions intersected by active faults. This increased exposure means that even moderate earthquakes can produce disproportionate consequences. Forecasting efforts have attempted to quantify this evolving risk. In 1999, the United States Geological Survey reported a 70% probability that one or more earthquakes of magnitude 6.7 or greater would occur in the San Francisco Bay Area before the year 2030. This estimate reflects not a single impending event, but a cumulative likelihood across multiple fault segments. It underscores the expectation that seismic activity in the region will continue to manifest through earthquakes capable of causing significant damage. The mechanics underlying these forecasts rely on a combination of historical records, geological observations, and modern instrumentation. Measurements of ground deformation using techniques such as GPS reveal that the fault system continues to accumulate strain at rates consistent with long-term tectonic motion. This ongoing deformation is a direct consequence of the relative movement between the Pacific and North American tectonic plates. The San Andreas fault system accommodates this motion, but it does so in a manner that alternates between gradual creep and sudden rupture. Understanding the distinction between these modes is critical. Some segments of the fault exhibit creeping behavior, where movement occurs slowly and continuously, reducing the likelihood of large earthquakes. Other segments remain locked, storing elastic energy until it is released abruptly. The 1906 rupture primarily involved locked sections that had accumulated significant strain over centuries. Identifying which segments are currently locked and how much stress they have accumulated remains a central challenge in earthquake science. One of the more revealing aspects of the 1906 earthquake is the variation in slip along the fault. The northern segments experienced larger displacements than the southern portions, indicating that the release of strain was not uniform. This uneven distribution raises questions about how stress may have been transferred to adjacent segments. Did the rupture relieve strain in some areas while increasing it in others? How do these interactions influence the likelihood of subsequent earthquakes on neighboring faults? The rupture that unfolded along the San Andreas Fault in 1906 did not begin as a singular break, but as the culmination of a long period of strain accumulation distributed unevenly through the crust. At its core, the system reflects the interaction between the Pacific Plate and the North American Plate, two massive lithospheric blocks moving laterally past one another at a rate of roughly 2 inches per year, or about 5 centimeters annually. That motion is steady at the plate scale, yet the fault itself does not accommodate it smoothly. Instead, large sections remain locked, resisting motion due to friction, while adjacent regions may creep slowly. This mismatch between continuous plate motion and intermittent fault slip is the engine that drives major earthquakes. In the decades and centuries leading up to 1906, stress accumulated elastically in the rocks surrounding the locked segments of the fault. This process can be visualized as a gradual distortion, where the crust on either side of the fault is bent and strained without immediate failure. Over time, the stress reaches a threshold determined by the frictional strength of the fault interface. That strength is not constant. It depends on factors including rock composition, temperature, pressure, and the presence of fluids within the fault zone. Once the accumulated stress exceeds this threshold at a critical point, rupture initiates. The initial failure during the 1906 event likely occurred near the northern segment of the fault, close to the offshore region west of San Francisco. From that point, rupture propagated bilaterally, tearing through the crust both northward and southward. The propagation speed, estimated at about 2.7 kilometers per second, reflects the rate at which stress was transferred ahead of the rupture front. This speed is governed by the elastic properties of the surrounding rock, and is typically a fraction of the shear wave velocity in the crust. As the rupture advanced, it released stored elastic energy in the form of seismic waves. These waves include primary waves, which compress and expand material in the direction of travel, and secondary waves, which shear material perpendicular to the direction of propagation. Surface waves, generated as energy interacts with the Earth's surface, contributed significantly to the destructive shaking experienced across the region. The duration of shaking, extending close to 1 minute in some areas, was a direct consequence of the extraordinary rupture length. A critical aspect of the 1906 earthquake lies in the concept of slip heterogeneity. The displacement along the fault was not uniform. Instead, it varied significantly from one segment to another. Near Point Reyes, surface offsets reached approximately 20 feet, while deeper sections experienced even greater displacement. Farther south, the slip diminished, indicating that the release of strain was concentrated in certain regions rather than distributed evenly along the entire rupture. This heterogeneity is influenced by variations in fault geometry and material properties. Fault geometry plays a decisive role in controlling rupture behavior. The San Andreas Fault is not a perfectly straight line, but a complex structure with bends, stepovers, and branching segments. These geometric irregularities act as barriers or facilitators to rupture propagation. A bend in the fault can increase normal stress, effectively clamping the fault and inhibiting slip. Conversely, releasing bends can reduce normal stress, making it easier for rupture to continue. In 1906, the rupture successfully navigated multiple geometric complexities, suggesting that stress levels were sufficiently high to overcome these barriers. The presence of fluids within the fault zone introduces another layer of complexity. Fluids can reduce the effective normal stress acting on the fault by increasing pore pressure, thereby lowering frictional resistance. This mechanism can facilitate slip even when the overall stress is relatively modest. Evidence from modern fault studies indicates that fluid pressure variations can influence both the timing and extent of rupture. While direct measurements from 1906 are not available, the behavior of the fault suggests that fluid processes may have contributed to the initiation or propagation of the event. Thermal conditions at depth also influence fault dynamics. As depth increases, temperature and pressure rise, altering the mechanical behavior of rocks. At shallow depths, rocks tend to behave in a brittle manner, fracturing abruptly when stress exceeds strength. At greater depths, ductile deformation becomes more prominent, allowing rocks to flow rather than fracture. The transition between these regimes defines the seismogenic zone, the part of the crust where earthquakes are generated. The 1906 rupture primarily involved this brittle zone, extending to depths where sudden slip could occur. Another key mechanism is the process of stress transfer. When a large earthquake occurs, it does not simply release stress locally. It redistributes it throughout the surrounding region. Some areas experience a reduction in stress, while others may see an increase, bringing them closer to failure. This redistribution can influence the likelihood of subsequent earthquakes on adjacent fault segments. Following 1906, certain sections of the fault system likely experience stress loading, setting the stage for future seismic activity. This process becomes particularly relevant when examining the broader fault network in Northern California. The Hayward Fault and the Rogers Creek Fault are not isolated structures, but part of an interconnected system. Stress changes induced by one rupture can propagate through this network, altering the mechanical state of neighboring faults. This interconnectedness complicates hazard assessment, as the behavior of one segment cannot be fully understood in isolation. The concept of seismic cycles provides a framework for interpreting these processes. Each cycle consists of a period of stress accumulation, followed by a rapid release during an earthquake, and then a renewed phase of accumulation. The duration of each phase can vary widely, influenced by factors such as slip rate, fault strength, and external perturbations. In the case of 1906, the release phase was exceptionally large, resetting stress levels along a significant portion of the fault. However, the accumulation phase resumed immediately, driven by ongoing plate motion. Modern observations have revealed that not all stress is released during a major earthquake. Residual stress can remain on the fault, particularly in segments that experience lower slip. This incomplete release means that some portions of the fault may be closer to failure than others, even immediately after a large event. Over time, differential accumulation further accentuates these variations, creating a complex mosaic of stress levels along the fault. Seismic wave radiation during the event also provides insight into the rupture process. The energy released was not uniform in all directions. Instead, it exhibited directivity, where waves were amplified in the direction of rupture propagation. This phenomenon can result in stronger shaking in areas aligned with the direction of rupture travel. In 1906, the northward propagation likely contributed to significant shaking along the Mendocino coast, while southward propagation affected regions closer to San Juan Bautista. Ground motion characteristics are further influenced by local geological conditions. Sedimentary basins, for example, can amplify seismic waves, increasing both the intensity and duration of shaking. In contrast, regions underlain by solid bedrock may experience less amplification. The distribution of damage in 1906 reflects these variations, with certain areas experiencing disproportionately severe effects relative to their distance from the fault. The recurrence of large earthquakes on the San Andreas Fault is governed by the balance between slip deficit and slip release. Slip deficit refers to the amount of displacement that has accumulated but not yet been released. Following 1906, the fault experienced a significant reduction in slip deficit along the ruptured segments. However, continuous plate motion has been rebuilding this deficit ever since. The rate of accumulation, combined with the historical record of past events, informs estimates of future probability. Trenching studies have extended this record beyond historical observations, revealing a sequence of past ruptures spanning thousands of years. These records indicate that while the average interval between large earthquakes may be on the order of a few hundred years, the actual timing can vary significantly. Some intervals are shorter, others longer, reflecting the inherent variability of the system. This variability underscores the challenge of forecasting specific events. Advances in geodetic monitoring have provided a more detailed picture of current deformation. Networks of GPS stations measure ground movement with millimetre precision, capturing the gradual accumulation of strain across the fault system. These measurements confirm that the relative motion between the Pacific and North American plates continues unabated, ensuring that stress will continue to build. Seismological data from smaller earthquakes offer additional clues. Microseismic activity can illuminate the structure of the fault and identify zones of weakness or increased stress. Patterns of seismicity may also indicate areas where stress is being concentrated. However, the relationship between small earthquakes and large events remains complex. While clusters of smaller quakes can precede major ruptures in some cases, they do not provide a reliable predictive signal. As urban development continues to expand across Northern California, the implications of these fault dynamics become increasingly significant. Infrastructure, population density, and economic activity have all grown substantially since 1906, amplifying the potential impact of future earthquakes. Even events smaller than 1906 can produce widespread disruption when they intersect with modern urban environments. The fault system beneath California remains active, driven by forces that operate on timescales far longer than human experience. The processes that led to 1906 have not ceased. They continue to shape the ground in subtle but persistent ways. Each year of accumulated strain brings the system incrementally closer to future ruptures, the timing and magnitude of which remain uncertain but inevitable within the framework of plate tectonics.